Hello.
Yeah.
Uh, so we'll start with the second session of the binary search. So let's recap what we have done in the previous session. The steps involved in solving a binary search problem is identifying the search space LR and what is the condition and what is the return value. This is just a recap. So I'll be moving fast. The problem statement will be like this: minimize k, subject to a condition k is true. So the way of identifying a binary search problem is you need to look for monotonicity. To be more precise, condition k creates that monotonicity. So this session focuses on more reinforcement of the concepts of binary search by solving two problems. Let's start with problem 1. The problem statement goes as below. Given a vector weights and number of days d, we need to find the least weight capacity of the ship that will result in all the packages. The packages weights are given in vector weights being shipped within d days. So we need to find the least weight capacity of the ship that will result in all the weights packages being shipped within d days. Okay, let's get into solving this problem. So the first step is identifying the search space. So identifying the search space is the step we are starting with. So there are two cases we need to consider. What happens if the capacity k of the ship is sum of weights more specifically if k is greater than or equal to sum of weights. All the packages are shipped in a single day. So when the capacity is the sum of weights, that means we have the packages, all the packages can be shipped within a single day. And the second case is when capacity k is less than max of weights. What do we have here? K is less than, sorry, here it will be greater than or equal to. So less than max weights what happens here is at least one of the items cannot be shipped. So here we can conclude that K lies between capacity K lies between max of weights and sum of weights. So hence we can say that the search space of the capacity is max of weights to sum of weights. So the next thing we'll do is look at the condition. So what is the condition? Yeah. So before we proceed to condition, we need to identify the monotonicity of the problem. Once we have identified the monotonicity, from there we can identify what is the condition. Let's look at the monotonicity problem. Is there a condition which is monotonic? Yes, we do have a condition which is monotonic. So I'll state it as here. So the weights are shipped in D days with capacity K. Let's assume that we are given this statement. What this implies is weights can be shipped in K plus, that is K, let's keep it as K star. K star is greater than K. So what is this monotonic condition we have here? If we are given that the weights can be shipped in D days with capacity K, we can say that the same weights can be shipped in D days with more capacity. So once we have checked that, once we are sure that weights can be shipped with a certain capacity, if we have a higher capacity, it automatically says that we can ship all the weights with a given D days. So from this monotonic condition, what is this question we need to ask? Given the capacity K, can we ship the weights in D days? So this is the question. and this is the condition we are looking at. We can say this as is feasible with capacity K returning Boolean. So let me reiterate this statement. So initially we have looked at the search space. By looking at two conditions, we have identified the search space, and now we are looking at the condition which makes us confident saying that this can be solved using a binary search. Is the first thing is we look at a condition which is monotonic. The monotonic condition is that the weights, given that the weights are shipped in D days with the capacity K, we are sure that the weights can be shipped in the same D days with higher capacity. So the condition says that given capacity K, can we ship all the weights in D days? That is the condition. So how do we write this function is feasible given capacity K? We'll just look at it. The first step is calculate the number of days required to ship all the packages. The thing which we have not mentioned here is we are considering the given capacity K. So using the given capacity K, let me write it here again. Using the given capacity K, calculate the number of days required to ship all the packages. So let us call this as dmin. Okay. All right. Let's keep it capital D because we have set this capital. Okay. Yeah. So once we have identified that the number of days required to ship all the packages is dmin with the given capacity, we will compare if the dmin is greater or less than with the given D. If D is greater than dmin, then what we can say is we can ship all the packages with capacity K. Since the number of days required to ship all the packages with the given capacity K is smaller than that given number of days, allowable days, which is the upper limit, we have even smaller number of days required. So we can say that as D is greater than dmin, we can say that we can ship all the packages with the capacity K. Alright. What happens in the other case? So else we'll say we can say that it is not possible. Alright. So this is the high level view of the algorithm. So going at the code goes like this: is feasible with capacity K. We start with number of days as 1 and total weight is 0 initially. So this total weight will increase as the number of weights are being introduced, and once it exceeds the capacity, we reset it and then we go forward. Let me write it. So for weight, in weights, total plus equals weights if total is greater than capacity K, then total is reset to weight. So here it is weight. Total is reset to weight and number of days are incremented. So once we are end of this loop, what we have is the days gives the number of days required to ship all the packages with the given capacity K. So now what we do is compare days with capital D, which is the parameter given. We return true, else return false. So this is the broad overview how we write code about for this problem. So this is the condition. Here we have gone through these major steps, and there is a finishing touch we require, which is the binary search algorithm. Let us finish the problem. So the program is whether we'll ship, can we ship in D days. So the first thing is search space, that is L comma R. What is this? Max of weights and sum of weights. And the second step is, what is the condition? Condition is feasible with capacity K. So what we'll be returning is L, because we want a feasible so L, after the algorithm finds minimum, L will return the minimum feasible point in the search space which satisfies the condition. So since we want to find a feasible capacity, a minimum feasible capacity, we want to return L. So we will be returning L since we want to find minimum capacity K which satisfies the condition is feasible capacity K. All right. This is the broad thing. Let's write the algorithm. Ship in days D, and the inputs are weights, array weights, and the permissible number of days D. So we can say LR is equal to max of weights and sum of weights. So once we have said this, we can just copy the template. So this is our template. Let's just copy it. All right. Yeah. So our condition, the next thing we'll do is just directly go at the condition and check the condition on mid. So the condition is feasible, and we'll just paste it here. And yeah, here is our code. The first step is, let's just highlight the things we did. We have identified the search space. We have identified the condition, and we have identified the return value. Yeah. So this completes the problem 1. Let's look at problem 2. The problem statement is as below. So this problem goes like this. So we are given an array nums. We want to split array nums into m subarrays. So what is a subarray? Subarray is continuous elements in the array, given array nums. So if we have an array 7, 2, 5, 10, 8, let's take an even simpler example. Let's have an array nums 1, 2, 3, 4, 5. A subarray is something which is continuous. We can take 2, 3, 4 subarray as continuous. So we can say it is a subarray. We can say 1, 2, 5, although each element is present in the array. Since they are not continuous, it becomes a subsequence rather than a subarray. So all we are looking at is, we want to split the array into m subarrays. So let the subarrays, the set of subarrays is S. S contains all the subarrays indexed A1 to AM. And we want to find the minimum of L. And L is defined as the maximum of the sum of all the subarrays. Such is the problem. Do we really think of various strategies of solving these problems? And wonder what this problem can be solved using binary search. Alright. Let's follow the similar steps from the previous algorithm. Okay. Okay. Yeah. So let's repeat the problem statement. Given an array nums, we divide the array into subarrays, m subarrays. S is the set of all the subarrays. L is defined as the maximum of sum of. So given an array of sum of all the subarrays, the maximum of it is L, and we want to find the minimum of L. This is the problem statement. Let's start with looking at the search space. Yes. So what happens if L sum, which is L is greater than or equal to sum of nums? So the immediate question which comes to our mind is number of subarrays we need. So the number of subarrays needed is 1. So since the maximum of the sum of all subarrays is the sum of the given array nums, we can say we just need one subarray. We need just one subarray, that is S is nums. Alright. So we are just setting the tone for the problem by identifying the search space. We need a second condition. So what does our second condition should be? Our second condition should be in such a way that we look at So what happens if the L is less than the max of nums? So if the maximum of array of sum of all the subarrays is less than the maximum of any of the elements in numbers, we can say that at least one of the subarray has a sum that has greater than L. To be very specific, any subarray which has max of nums has a sum greater than L. So at least one of the subarrays has a sum greater than L. So our desired L lies between max of nums and sum of nums. So let's go through these steps once again. So the first step is identifying the search space. So there are two conditions we are looking at. What happens if okay. So L contradicts with the written value. So let's keep it L sum. L sum All right. So what happens if L sum is greater than sum of all the numbers given? All we need is a single subarray, and the set of subarrays will be a single element, contains a single element. The cardinality of S will be 1, and the element present is the given array. And what happens if L is less than maximum of the given numbers? We can say that at least one of the subarrays, to be more specific, any subarray which contains max of nums will have a larger sum than L sum. By this we can say that the desired or search space will be ranging from max of nums till sum of nums. Okay, so the second and the crucial step of the binary search is finding the condition. So what is the condition? And by this we need to carefully understand the problem and then go forward. The monotonic condition we are looking at is, let us form the premise. The premise will be very simple. Just assume that we can split nums into m subarrays given by S is A1, A2 till AIM. Okay, such that the sum of AI is less than or equal to T. What is T? Let's make it a threshold T. So this is our premise. So let's assume that we have a threshold T which is in our search space, and we have all the subarrays of the given array sums. The sum of all the subarrays of the given array sum is upper limited by threshold T. So let's say we have such an instance, then we can say that we can split the same array with threshold T star greater than or equal to T. So let's say, because we already have an instance, let's say T star greater than T. So increasing the threshold doesn't harm us. So this is the monotonic condition, and a similar monotonic condition is present in problem 1 as well. So by looking at this monotonic condition, we can derive the question to be which acts as a condition in our binary search problem. So what is the condition? So given the threshold T, can we split the array nums into m subarrays such that the sum of ai is less than or equal to t. So this is the condition. So what we have done here, we have derived the condition by carefully observing the problem and finding a condition which is monotonic, and then posing a question which acts as a condition for our binary search problem. Let's give it a name. Can split given threshold t and returns a boolean value whether we can split the given number of given array nums into m subarrays such that the sum of the subarrays is upper limited by the threshold t. So let's look at writing the algorithm for the condition. So what is the condition? Can split input is threshold t, which is a number, it's a natural number. Okay, the first thing we do is find the minimum number of subarrays possible such that the sum of the any subarray is upper limited by the threshold t. Let's write it. So given threshold t, calculate minimum number of subarrays the condition is such that sum of ai is less than or equal to t. Okay. So let's call this as m min. Okay. M. Okay. So what happens if m is greater than m min? What we can say is we can split the array nums into m subarrays. Since with the given threshold t, which acts as the upper limit for the sum of the subarrays, we have got a smaller number of subarrays, so we can just increase the number of subarrays, and the resulting sum of the subarrays will be even smaller, thus leading even better case. So we can do this. We can split with even more number of subarrays, but what happens in the other way is it's not possible. So we will not be able to do that. So let's write the code for this. It will be can split threshold. So in the place of days we have count. Count will give us in the end, after this loop we have m min, this is count, and this is the total. Total includes the numbers. So once the total threshold is t, once the total exceeds the threshold t, we reset it to num and increase the count. So just to avoid the confusion, we can say m underscore min and use the same notation. Sorry. Okay. Total. Okay. When m min is greater than okay, there was a problem. Days give us d min, when d min is greater than d, we return false. Yes, return true. Sorry, my bad. That was just typo, and let's do that here again. Alright, so once we have coded the condition, all we are left with is finishing the problem with the binary search algorithm. So what we have is, can we split into m subarrays? Okay, split down a little bit wider. Okay, so what is the search space? Max of nums. This is the easiest part of the writing the code. So can split is our with given threshold t, and again we will be returning L because we want to find the minimum threshold t. Threshold t which satisfies our condition can split threshold t. Okay, let's finish the problem. Max of nums, sum of nums, and our condition is can split. Yeah. This finishes our session. Let's quickly recap. In the last time we just got a quick idea of the template and what are the different steps involved in writing the algorithm. We have quickly looked at 3 questions. The steps involved are identifying the search space and what's the condition and what is the return value. So this second session focuses more on the condition. How do we get the condition which plays a crucial role in setting the problem which needs to be solved, and setting the problem into our binary search type of problem. So once we have the condition set, let's look at problem 1. If we have the condition set, it's pretty easy to write the algorithm, because the search space is defined and the condition is defined. These are the two steps which play a key role in writing the algorithm. In most situations, the search space will be clear because you will be just looking at what are the different possible values of the return value. So let's say you are asked to return something, you are asked to minimize something, or you are asked to maximize something. You know the ranges of what you need to find, but the crucial step, what is the crucial step in making the given problem into our binary search problem is the condition. A monotonic condition which allows us in posing a question which acts as a condition for our problem. So we have looked at two questions and we have focused on finding the condition which plays a key role, and then written the code, which is a simple step. So in the next coming session, we'll look at even more similar type of questions involving binary search, as these two problems are not very clear, which is not evident as before. In the first session, we have problems which are very evident, and in the first look, an average programmer can identify it, saying that this problem can be solved using a binary search problem. But the questions in this session, these two problems, is not very clear. So it requires a bit of analysis, and this analysis forms the crucial step in finding out the condition, which plays a crucial role in turn in writing our binary search algorithm. Thank you.